The world learned how to make airplanes fly and even break the speed of sound. But keeping a giant machine completely frozen in the sky, that turned out to be a challenge of an entirely different level. At first glance, it sounds simple. Install a more powerful engine, blast air downward, and the aircraft should hover effortlessly above the Earth. But reality works very differently. The instant forward motion stops, the familiar laws of aerodynamics begin turning against the machine. Nature itself seems to resist this idea, setting invisible traps most people never even realize exist. Today, we'll uncover why even enormous engine power cannot allow a helicopter to simply hang motionless in the air. You'll see the hidden limits of these incredible flying machines, the terrifying aerodynamic dangers pilots face, and the brilliant engineering tricks that once allowed humans to seemingly outsmart gravity itself. We travel back to the year 1907. Engineers across the world are obsessed with one dream: building a machine capable of rising straight into the sky. French inventors such as Paul Cornu and the Breguet brothers create the earliest prototypes. On a dusty testing field stands a strange structure made from metal tubes with a gigantic rotor mounted above it. The engine roars to life. A deafening mechanical scream fills the air. The blades spin faster and faster, throwing clouds of dust across the ground. And suddenly, the impossible happens. The machine lifts nearly 1.5 meters into the air. For a brief moment, it looks like victory. Then disaster strikes. The second the aircraft loses contact with the ground, the heavy fuselage begins spinning violently in the opposite direction of the rotor. Faster and faster, it twists. The pilot instantly loses all sense of orientation. Centrifugal force throws the aircraft sideways. The blades smash into the earth, and the entire structure collapses into wreckage. Again and again, the same terrifying accidents repeat themselves. Experimental helicopters spin uncontrollably around their own axes. Newspapers publish mocking headlines. Journalists declare vertical flight impossible. Some believe the strange aircraft shapes create invisible air whirlpools that twist the machines apart. Others blame mysterious magnetic fields or destructive engine vibrations. People begin believing that vertical flight will remain only a fantasy on paper. But the true problem had nothing to do with mysterious anomalies. The real enemy was something much simpler: Newton's third law. For every action, there is an equal and opposite reaction. The giant main rotor pushes enormous force against the air to spin in one direction. In response, an equally powerful reactive torque tries to spin the helicopter fuselage in the opposite direction. To defeat this problem, engineers create a second system. At the end of a long tail boom, they install a much smaller rotor. Unlike the main rotor, this one pushes air sideways. Its thrust is carefully calculated to perfectly counteract the spinning force created by the main blades. Inside the cockpit, 2 pedals appear beneath the pilot's feet. Pressing left or right changes the angle of the tail rotor blades, increasing or decreasing sideways thrust. The tail boom effectively becomes a giant lever that stabilizes the entire aircraft. But preventing the helicopter from spinning is only the beginning. The greatest aerodynamic challenge appears the moment the aircraft stops moving completely. Year 2015. A rescue operation unfolds beside a steep cliff. Far below lies freezing water. Several people are trapped on a narrow rocky ledge. Airplanes cannot reach them. Boats cannot approach through the sharp rocks below. Then a helicopter appears overhead. The aircraft approaches the cliff and suddenly stops dead in the air. 4 tons of metal now hover motionless above empty space. The downward blast from the spinning blades bends trees beneath the aircraft. Inside the cockpit, the pilot constantly makes tiny, incredibly precise movements with both hands and feet. The helicopter neither rises nor falls. It does not drift left or right. To the people watching below, it looks almost supernatural, as if gravity itself has temporarily stopped working. This illusion has created countless misunderstandings. Many people online are convinced helicopters possess some secret maximum thrust hovering mode that creates an invisible cushion of pressure beneath the aircraft. Others believe giant hidden gyroscopes somehow fight gravity through rotation. But the real answer is even more fascinating. A helicopter pilot does not mainly control altitude by increasing engine speed. The engine usually maintains nearly constant RPM at all times. The true control system lies inside an incredibly sophisticated mechanism that changes the angle of the rotor blades themselves. Beneath the rotor sits a complex assembly called the swashplate system. When the pilot raises a control lever known as the collective, the mechanism rotates all the blades simultaneously around their own axes. This changes their angle against the airflow. The steeper the blade angle becomes, the more air the rotor grabs and forces downward. More downward airflow means greater upward lift. Ironically, hovering is one of the most demanding situations for the engine. During forward flight, incoming air naturally assists the rotor system. But while hovering, the helicopter must create all lift entirely on its own, consuming huge amounts of fuel in the process. The pilot continuously adjusts blade pitch so the lift force perfectly matches the aircraft's weight. Only in this delicate balance can the helicopter remain suspended motionless in the sky. But this balance is dangerously unstable. A single mistake during vertical descent can destroy that stability instantly. Year 2014. Spectators watch a helicopter demonstration flight. The aircraft hovers steadily, 100 meters above the ground. The pilot begins a dramatic vertical descent toward the landing zone. At first, everything appears normal. Then suddenly, the helicopter drops violently. The heavy machine plunges downward almost uncontrollably before slamming into the ground in a devastating impact that completely destroys the aircraft. Investigators later discover something shocking. The engine was functioning normally. The transmission system remained intact. Every critical component worked properly until the moment of impact. The helicopter crashed purely because of the surrounding airflow. Witnesses struggle to explain what they saw. Some blame invisible downdrafts. Others talk about dangerous low-pressure zones sucking the aircraft downward. Online theories even suggest communication towers disrupted onboard electronics. But the true cause was an aerodynamic nightmare known as vortex ring state. While hovering, a helicopter continuously pushes air downward beneath itself. If the pilot begins descending too quickly, usually faster than 300 meters per minute, while still applying power to the rotor, the aircraft starts falling into its own turbulent airflow. The descending air begins curling upward around the edges of the rotor disc and gets sucked back into the blades again. A deadly circular airflow forms around the helicopter. The rotor blades now spin inside highly turbulent air that is already moving downward. As a result, the pressure difference responsible for generating lift rapidly disappears. The helicopter begins shaking violently. Lift collapses. Control authority weakens. And the terrifying part is this: adding more engine power actually makes the situation worse because it strengthens the vortex itself. To escape, the pilot must immediately tilt the helicopter sideways or forward, forcing the aircraft out of its own disturbed air and back into clean airflow. Yet physics still provides one final lifeline, even if the engine fails completely. Year 2015. A routine training flight over mountainous terrain. The helicopter cruises at an altitude of exactly 1,000 meters. Then suddenly, a loud mechanical bang erupts from the engine compartment. The turbine dies instantly. The helicopter is now powerless high above the ground. To most people, survival would seem impossible. But instead of falling like a stone, the helicopter stabilizes itself and enters a controlled descent. Moments later, it lands safely in an open field. The landing gear survives intact, and the crew calmly walks away without injuries. Incidents like these often spark wild theories. Some believe helicopters contain hidden emergency systems that fire compressed air moments before impact. Others imagine giant shock absorbers buried inside the fuselage. The real explanation is one of the most brilliant survival mechanisms ever designed into an aircraft. It is called autorotation. At the heart of the system sits a special device called a freewheeling clutch. The instant the engine fails, the clutch disconnects the dead engine from the rotor system. This prevents the heavy engine from slowing the spinning blades. The pilot must react within seconds by lowering the collective completely, flattening the blades. Now, the helicopter begins falling, but as it falls, air rushes upward through the rotor from below, forcing the blades to keep spinning freely. The helicopter essentially transforms its falling energy into rotor energy. Near the ground, the pilot performs a carefully timed maneuver called the flare, pulling the nose upward to rapidly reduce speed. Then, in the final seconds before touchdown, the pilot sharply increases blade pitch. The spinning rotor grabs huge amounts of air, generating one final burst of lift that softens the landing just enough for survival. This procedure is standard helicopter pilot training. But even these aerodynamic principles begin failing under truly extreme conditions. Year 2005. Test pilot Didier Delsalle prepares for a mission many experts consider physically impossible. On May the 14th, he pilots a lightweight helicopter toward the summit of Mount Everest, 8,848 meters above sea level. Temperatures there fall to -35 degrees Celsius. Winds can exceed 120 kilometers per hour, and the air itself becomes dangerously thin. Yet Delsalle does not simply fly past the mountain. With extraordinary precision, he carefully lowers the helicopter directly onto the tiny, frozen summit of Everest itself. According to official aviation rules, he must remain there for at least 2 minutes for the landing to count. He remains for more than 3. When footage of the event is released, many experts immediately accuse it of being fake. Some claim the videos must be computer-generated because the physics simply do not seem possible. At that altitude, atmospheric pressure is only about 1/3 of sea level pressure. The air is so thin that rotor blades struggle to generate enough lift at all. Meanwhile, turbine engines suffer severe oxygen shortages and lose enormous amounts of power. Under normal conditions, the helicopter should barely be able to fly. The skeptics were correct under ordinary circumstances. To make the mission possible, engineers transformed the helicopter into an ultra-lightweight machine. Every unnecessary kilogram was removed. Passenger seats disappeared, soundproofing vanished. Interior panels and non-essential equipment were stripped away entirely. The aircraft lost over 120 kilograms of weight. The pilot wore a heavily insulated suit and oxygen mask because the cabin itself was no longer fully sealed. The engine operated at the absolute edge of safe temperatures. The composite rotor blades spun near maximum allowable speed to compensate for the thin air. Even a tiny control mistake could have caused compressor stall and total engine failure. This mission revealed the absolute limit of the traditional helicopter design built around one main rotor and one tail rotor. After that, engineers began radically redesigning helicopter technology itself. Today, entirely new helicopter designs are appearing more frequently. Some hover above crowded cities with remarkable stability. Others maneuver through narrow mountain valleys or lift enormous construction loads in tight spaces. But one detail immediately stands out. Many of these aircraft no longer have tail rotors at all. Their tail booms are completely smooth, with no spinning blades anywhere on the rear section. Yet somehow, the fuselage still remains perfectly stable instead of spinning uncontrollably. To observers, it almost looks like the aircraft is breaking the laws of physics. This mystery sparked countless theories online. Some people proposed hidden electromagnetic stabilizers. Others imagined giant gyroscopic systems buried inside the aircraft. But the real answer, once again, comes from aerodynamics. Engineers developed a system called NOTAR, short for no-tail rotor. Inside the hollow tail boom sits a powerful fan driven directly by the main engine. This fan pumps high-pressure air through the boom continuously. The air exits through tiny slots along the side of the tail boom and flows smoothly around its curved surface. Thanks to a phenomenon called the Coanda effect, this airflow creates a pressure difference that generates sideways force, counteracting the rotational torque from the main rotor. Another revolutionary solution is the coaxial rotor system. Instead of one main rotor, these helicopters use 2 large rotors mounted above one another on the same mast. They spin in opposite directions, meaning the torque from one rotor perfectly cancels the torque from the other. As a result, no tail rotor is needed at all. The aircraft becomes shorter, more compact, and often more maneuverable. Over time, engineers learned how to neutralize reactive torque, survive total engine failure using pure aerodynamic energy, and stabilize multi-ton aircraft using invisible pressure forces instead of spinning tail rotors. A helicopter hovering motionless in the sky is not a violation of nature. It is the result of unbelievably precise mathematics, engineering, and aerodynamic balance. Every second, a helicopter remains suspended in the air. Countless invisible forces are fighting each other in perfect equilibrium.